We detect light with photomultipliers. Now, I'm sure that you've learned this already in school. So we detect photons through the photoelectric effect. All right? So what is a photoelectric effect? A photon hits the cathode plane and emits an electron. And we capture that electron.
Thank you.
That's all we do. All right, so photocathodes are generally made of antimony or alkali metals. And then what happens is, so here's a photon, comes in, photoelectric, or, you get the photon here, scintillates, capture the photon, here's the photocathode, and here's this one electron. You start out with one electron. And then the one electron is amplified through these series of dynodes. All right, so you start out and then you have cascades. So this one electron then liberates, say, 2, 3, or 4 electrons, and then you have this cascade so that at the end you have a reasonably sized signal. The quantum efficiency is, of course, not 1. So not every photon that hits your photocathode will give you an electron. And that's what we call the quantum efficiency. It's the number of photoelectrons over the number of photons. So normally this is about a quarter. So you need 4 photons to liberate 1 electron. Now, as I mentioned, you amplify the signal through a series of dynodes. And the secondary emission normally has a coefficient of about 4. So every electron that hits a dynode will liberate 4 electrons in turn. So if you want to have a multiplication of your signal of a factor, say 1,000,000, how many dynodes do you need?
A lot.
So, that's not a reasonable answer. So, if you want to have, m is 1,000,000, with each time you have an amplification of a factor of 4, you need 10 dynodes. Because 4 to the power 10 is about 10%, about 1,000,000. Now, these photomultiplier tubes, I'll show you some. They come in all shapes and sizes. And these are used everywhere here at the lab to detect photons. So here's one. So this is a window. Photon comes through. You can see the photocathode. And then you see a very nice spider web that will capture the electron that is liberated and then amplify it. And there is an open one that shows you actually the series of dynodes where you will have the multiplication of the signal. And this one is a phototube that we use, as I said, they come in all shapes and sizes, that we use in a neutrino experiment, also down the street here, for mini boom. And again, you can look at this, I won't pass this around. You can look at it during the break. Again, you see the photocathode and then the mechanism to capture the electrons. By the way, this is exactly the converse of something that you use in your home all the time. This is the converse of, a light bulb. Because in the light bulb, what you do, you pass a current through, you get light. Here you capture the light, you get a current. Okay, how do we detect photons? I've told you already one way to detect photons is the photoelectric effect. The other 2 ways is a photon can simply scatter off an electron. So you can see this electron that in turn will ionize the medium. Or you can have pair production, where a photon can turn into an electron-positron pair. So, now we look at interactions of electrons with matter. Remember, this is the EDX formula, how much energy a particle loses per unit length. That formula does not hold for electrons. Why? Why? Remember the analogy with bowling?
We're barely getting there.
Correct. So with electrons, it's like going bowling with a baseball. Because electrons would interact with the electrons of the atoms. They have the same mass, right? So that formula does not hold for electrons. So for electrons, there's a different mechanism. Electrons are subject to Bremsstrahlung, which means that in the field of a nucleus, as soon as they experience the field of the nucleus, what they will do is they will start radiating photons. Now, as a consequence, if an electron interacts with matter, you get a cascade, all right? So, simplistically, here's say an electron that comes in, radiates a photon, and I told you a photon could pair produce a positron and an electron, and you get these whole cascades. So this is a simulation of what happens if an electron, in this case an ATGeV electron, hits a crystal.
It's like cancer.
So you create this cascade of particles, this shower of all kinds of particles that be captured. That's how we detect electrons. And even if this were a photon, that's how we also detect photons. Because there will be no track, but the mechanisms are identical. So now we go to hadrons. How do hadrons interact with matter? I told you these quarks. Now, these processes are much more involved than electromagnetic cascades. And I won't go into any details. There are two components of this. There's a hadronic component and an electromagnetic component. But in general, they also create showers of particles. But showers that are much less well behaved than electrons. They have larger fluctuations. And the technique that we normally use to measure the energy of electrons, photons, and hadrons is generally destructive. That means you want to stop the particle and measure all their energy. And the device for measuring the total energy is called a calorimeter. Now, there's one other detection technique that is used all the time at the lab. And before I discuss that, let me ask you a question first. Can you go faster than the speed of light? No. Yes. Who said no? Only one person? Okay. You said no. Who said yes? You said yes?
There was an experiment that was tried in between going faster than the speed of light. There's an experiment undergoing that speed result that will cause, in theory, cause neutrinos to go faster than the speed of light.
Okay. I don't know about that experiment.
It's like a certain field where its speed is slower, you have to get something that's has mass to go faster.
Perfect. That's the perfect answer. Yeah, the question that I asked you was a trick question.